Now come to the second type of passive diffusion, that is osmosis. Osmosis is actually the movement of solvent across a permeable membrane. So it is nothing but a type of diffusion of the solvent molecules. What do you mean by that? For example, this is a concentrated solution that has the water particle and some sucrose molecule, sucrose or glucose molecule. Okay, so we know that this is a sucrose solution. So we know the sucrose concentration is higher. So sucrose is a solute here. So normally what happens in case of diffusion, the sucrose will move from higher concentration to lower concentration. Okay. But if we separate this sucrose solution via a semi-permeable membrane, okay, if we separate it via a semi-permeable membrane, at one side we place the water, other side we place the sucrose solution, and the membrane is not permeable to sucrose. So what will happen? But it is permeable to water. Then water is the solvent molecule. So water from higher concentration, it will move to the lower concentration. So movement of solvent particle from higher concentration to lower concentration is known as the osmosis. So osmosis is also a passive passive type of transport where no energy is utilized, because here the solvent is moving from high concentration to low concentration. So the concentration gradient of the solvent is important. But along with it, osmosis is proportional to the reflection coefficient of the membrane also. Okay, so what is reflection coefficient? It is the ability of the membrane to reflect the solute. It is known as the reflection coefficient. That we told that membrane is not permeable to solute. It is not permeable. But whether it is totally impermeable or some permeability is there, so that will be defined by the reflection coefficient. And this reflection coefficient, it actually varies from 0 to 1. Okay, so if the membrane reflection coefficient, it is 0. Reflection coefficient 0 means the membrane is permeable to, it is totally permeable to the solute. No reflection is happening. Okay, so it is totally permeable to the solute. That means there will be no osmosis here. And if the reflection coefficient means 1, that is complete reflection, all the solute particles will be reflected back. That means in that case, there will be the osmosis will actually happen. So the reflection coefficient is a number between 0 and 1 that describes the ease with which a solute permeates a membrane. If the reflection coefficient is 1, the solute is impermeable. Therefore, it is retained in the original solution. It creates an osmotic pressure and it causes the flow of solvent or water flow. Now, if the reflection coefficient is 0, that means solute is completely permeable. Therefore, it will not exert any osmotic effect and it will not cause water flow. So the osmosis, we can say, it is proportional to the concentration gradient of the solvent as well as with the reflection coefficient of the membrane. Now the tendency of the particle, solvent particle, now the tendency of for the movement of certain solvent particle to a region of greater solute concentration. So to the region of greater solute concentration. So in this direction the movement is happening. The solvent is greater here. So it will move to this direction. Now this can be prevented. The movement of this solvent can be prevented by applying pressure. By applying pressure to the more concentrated solution. So if we apply pressure here over here, and these hydrostatic pressure necessary to prevent the movement of solvent is known as the osmotic pressure of the solution. Okay, so the hydrostatic pressure necessary to prevent the osmosis, the movement of solvent from high to low concentration, is known as the osmotic pressure. So when we are studying osmosis, we need to know about two things. One is the osmotic pressure, and osmotic pressure, it depends upon the concentration of the osmotically active particle. So we want to know how we will express the concentration of osmotically active particle. So one thing is osmotic pressure, another is the concentration. These two things we need to know. Now osmotic pressure, it is like the boiling point elevation or freezing point depression. It is a colligative property. Okay, so it depends on the number of particles rather than the type of particles in the solution. That is, it is a fundamental colligative property of the solution. In an ideal solution, osmotic pressure P is equal to, it is nRT divided by V, where P is the osmotic pressure and N is the number of particles, R is the gas constant, T is the absolute temperature, and V is the volume. Now, if the T is held constant, it is clear that the osmotic pressure, it is proportional to the N by V, that is the concentration. We can also call it the N by V, we can write it C. So, P is equal to C or T, the concentration of the particles. What type of particles? That is osmotically active particles per unit volume of solution. So now we must know how can we express the concentration of osmotically active particles per unit volume of solution. Now in chemistry, if we want to express the concentration of any solution, we will say it in terms of molarity, that is number of moles per liter. We know that the mole of 1 mole is equal to 6.023 into 10 to the power 23 number of particles. That is the Avogadro's principle. So now weight of 1 mole in grams, that is the atomic or molecular weight of that element in grams. For example, in case of sodium chloride, we will see that we know that the 1 mole of NaCl will be equal to their molecular weight will be 23 gram plus 35.5 gram. It is around 58.5 gram. Okay, and we know that 1 millimole is 1 by 1000 mole, 1000 of a mole. So we can convert it into this molar concentration into millimolar concentration. So 1 mole of NaCl, it is 58.5 gram. So 1 millimole will be equal to 58.5 milligram. Okay, so per liter can by this way we can express the concentration. But if this sodium in our body, inside our body, this sodium chloride will be in a solution. We have the blood plasma, where this sodium chloride will be ionized into two osmotically active particles. One is sodium, another is the chloride. So the pressure exerted by this osmotically active particle, the concentration of this osmotically active particle, it is better to express it in the terms not moles but the osmoles. Now what are the difference between these moles and osmoles? So there are difference if the particle is osmotically active, that means the sodium chloride. So when it will go to the solution, it will there will be two osmotically active particle, one is sodium, another is the chloride. Okay, so their concentration of osmotically active particle, it is doubled. But in case of glucose, you will see that glucose is not ionized, so the number of moles will be equal to number of osmoles here. Okay, so it is not osmotically active, so it will not ionize. So 1 mole of glucose will give rise to the same osmoles of osmotically active particle. Hence, to express the concentration of a solution in terms of number of particles, the unit called the osmole. It is used in place of grams. Now 1 osmole is 1 gram molecular weight of osmotically active solute. Thus 180 gram of glucose, which is 1 gram molecular weight of glucose, is equal to 1 osmole of glucose, because glucose will not dissociate into the ions. Conversely, if a solute dissociates into 2 ions, 1 gram molecular weight of solute will become 2 osmoles, because the number of osmotically active particles is now twice as great as in the case for the non-dissociated solute. Therefore, when fully dissociated, 1 gram molecular weight of sodium chloride, we know that we calculated, it was 58.5 grams, that is 1 mole NaCl per liter. It is 58.5 gram per liter, that is equal to 2 osmoles. Similarly, we know that that 1 mole per liter, millimole, if we express it in 1 millimole, then it will become 58.5 milligram. So 58.5 milligram is equivalent, will be the 2 milliosmole of sodium. Okay, so we actually express them in terms of osmoles per liter or osmoles per kilogram. So here we will come across with the two terms. One is the osmolality, another is the osmolarity. So number of osmoles per liter of solution, osmoles or milliosmoles per liter of solution, is known as osmolarity, whereas number of osmoles or milliosmoles per kilogram of water or solvent is known as the osmolality. As 1 kg of plasma is equivalent to 1 liter in our of plasma in our body, we usually use this term osmolarity, that is number of osmoles or milliosmoles per liter of solutions. Now how can we measure the osmolar concentration of plasma, or we can say the osmolarity of the plasma? Now osmolarity can be measured by this freezing point depression. What is this? Now the presence of solute in a solution, it lowers the freezing point of a solution relative to that of the pure solvent. For example, pure water, we know that it freezes at 0 degree centigrade. If one dissolves 10 grams of sodium chloride in 100 ml of water, the freezing point, it will go down to minus 5.9 degree centigrade. So in case of pure water, the freezing point is 0, but we make, if it is a solution containing some solute, that there will be depression of the freezing point. Now what is the freezing point depression of plasma? If we know it, then we can calculate the osmolarity of the plasma. It is seen that if we dissolve 1 mole of any substance in any solution, so the freezing point depression, it becomes 1.86 degrees centigrade. So 1 mole per liter or 1 osmole per liter, we can say that is equal to 1 mole means 1 osmole, that means 1000 milliosmole per liter. Okay, so we can say 1000 milliosmole per liter of a concentration of a solution, it depresses the freezing point by 1.86 degree. So 1 milliosmole per liter will depress the freezing point 1.86 divided by 1000, that is 0.00186 degrees Celsius. So we can say that the number of milliosmoles per liter in a solution equals to the freezing point depression divided by 0.00186 degrees Celsius. So that will give us the osmolarity. How it is giving osmolarity, we'll see. First, you remember that if we dissolve 1 milliosmole of solute in 1 liter of a solution, the depression of freezing point of that solution will be 0.00186 degrees Celsius. Now experimentally we have seen that blood plasma, it freezes at the freezing point depression, it is freezes at minus 0.54 degrees Celsius. So the freezing point depression is minus 0.54 in case of plasma. So we know that if the concentration is 1 milliosmole per liter, then freezing point depression is 0.00186 degree. So what point we can say in this way, 0.00186 degree depression of freezing point means 1 milliosmole per liter concentration. So 0.54 degree centigrade of depression of freezing point means 0.54 divided by 0.00186, obviously. So here we can say that the osmolarity of the plasma will be 290.3 milliosmole per liter, or we can say it 290 milliosmole per liter. It actually varies within a range 290 to 300 milliosmole per liter. So from this freezing point depression, we have generated the value of plasma osmolarity, that is 290 milliosmole per liter. Now, by measurement of serum osmolarity via this freezing point depression method, it is an experimental method, but clinically we usually use this formula, that is osmolarity is equal to 2 sodium, that is sodium is expressed in milliequivalent per liter, plus glucose concentration of our body, milligram per deciliter, divided by 2.8, plus blood urea nitrogen level divided by 18. So by this formula, clinically we have to measure the sodium concentration, glucose concentration and blood urea nitrogen concentration, and if we have these values available, so we can calculate the osmolality of the plasma, which is very much needed to know the hydration status of a patient. Now we know the osmolarity of plasma. From this we can calculate the value of osmotic pressure of the plasma. Okay, by this Van 't Hoff's formula. So from this formula we get that osmotic pressure of 1 milliosmole per liter is equal to 19.3 millimeter of mercury. And we know the osmolality of plasma, it is 300 milliosmole per liter. So 300 into 19.3, it is 5790 millimeter of mercury. It is a calculated value of osmotic pressure. But actually if we measure it experimentally, it comes around a bit less, that is 5500 millimeter of mercury. Why this difference happens? Because many of the ions in the body fluid, such as sodium ion, chloride ion, they are highly attracted to one another, so they cannot move entirely unrestrained in the fluid and create their full osmotic pressure potential. Okay, so that is the reason there is a gap between the calculated value of osmotic pressure and the measured value of osmotic pressure. These are the references, and thank you.